Hello and welcome back to the part 2 of the Geodict 2021 visualization workshop. In part 1 we learned how we can visualize gray value images, or rather volume images, as well as voxelized microstructures. In the upcoming part 2 we will use the knowledge from part 1 to visualize result fields from simulations in combination with microstructures. In addition, we will get to know further visualization options for result fields. We will then save our results with the GeoApp Easy Image. We pick up right where we left off and dive right back into Geodict. Before we start, I would like you to disable the advanced visualization features that we had enabled to produce our marketing images, because it will lead to faster update rates when we keep changing settings in this part too. For this purpose, please go to the Camera tab and disable Show Outlines, Show Halo, and Global Lighting. Now we can start with part 2. Geodict can not only display volume fields and microstructures alone, but also both in combination. Of course, this is necessary if we want to examine our simulation results on our microstructure. To demonstrate this, we will load the simulation result of a flow simulation done with Geodict simulation module FlowDict for this very structure we already used in part 1. We load the flow simulation result via the GDR result viewer. For this purpose, we can load the GDR file via the toolbar, the menu, or via drag and drop. For drag and drop loading, we open the workshop folder via Geodict's project folder icon and navigate to the subfolder part 2 and drag the file Lear-Stokes result.gdr into Geodict. The result viewer opens. The result viewer in and of itself with its features is almost worth an own workshop. Unfortunately, we can only go into a few basic features at this point. For a rough overview, we find here the Result tab under Report the results of the flow simulation in Z direction. In the Plots subtab we can also have a look at the existing plots for these data. In the Map subtab we find the input parameters used in Geodict for this simulation. With the Load Structure button up here, we can load our microstructures matching the simulation. The green dot over here indicates that we have already loaded the matching microstructure for the simulation. If the dot is colored red, the current structure does not match the simulation field. You must click Load Structure to load the correct microstructure to follow this workshop. Next, we go to the tab Flow Visualization. Here we can load our flow field in Z direction. Since we only simulated in Z direction, the X and Y directions are grayed out, we press Load. Geodict asks us now which components of the volume field we want to load. We keep all components checked in order to load all volume fields. We wait for a second till Geodict has finished loading. We close the result viewer and have a look at the visualization area. It appears as nothing has happened because the microstructure is obscuring most of the simulation, the volume field. To make sure that our volume field is there, we hide our microstructure briefly by clicking on the checked box in the Structure tab. Our volume field is loaded, but it looks a bit strange at the moment. This is because the settings of the color map from part 1 are still active. For a clean start, we go to the Volume Field tab and open the color map via the Edit button. We reset the color map to the built-in defaults down here and close the color map again. Let's have a quick look at the settings in the Volume Field tab here. We can see that the normalized field component velocity is currently displayed for the color parameter. This is the absolute flow velocity at any point in the field. Here we can also select and display the other field components of our simulation. For this workshop, we will select the field component velocity. Now we can show our microstructure again by checking the box in the Structure tab. Now before we really get started, we first ask ourselves, what do we want to show the viewer? In this case here, I would like to show how the flow moves through the pores of this porous grain structure. I would like to focus on the flow and thus communicate the characteristics of the pore space. However, I still want to integrate the microstructure discretely in order to maintain the connection between simulation and structure. In this way, we create continuity in the graphics narrative for the viewer. We start by choosing the colors of the microstructure more discreetly and muted. Since the colors of the volume field provide important information about the velocity in the pores, the focus should be there. If you would now choose colors for the material IDs, the viewer would not have a clear focus point. The importance of the information would be lost. Ultimately, however, we still want to have a certain contrast on the microstructure so that we can still recognize it. We solve this problem by choosing different shades of gray for the material IDs. To start, we open the Color and Visibility dialog. The color of the grains and material ID 1 can be left white. For the color of the grains and material ID 2, we choose light gray instead of the dark gray. For the color of the grains on material ID 5, we choose the dark gray. We use the dark gray that was previously selected for material ID 2. If you look at this, we can still distinguish the different grain sizes. However, the materials are no longer in fierce attentional competition with the result field, because we no longer have ambiguity color information. We close the Color and Visibility dialog again. Next, we take care to uncover the volume field. For this, we have the Clip function in the Structure tab. We open the Structure tab and have a look at the clipping section over here. The clipping controls the visibility of the component in the visualization area. Each axis, X, Y, and Z, has a start and end value that determines the visibility in positive and negative direction along the axis. The clipping can also be inverted here. This can be used to create all kinds of nice effects. In our case, we want to clip our microstructure along the Y-axis. To make it easier to orientate ourselves, we switch on the Axis Cross again in the menu View, Legends and Overlays and click Axis. Then we align our camera in the way we will need it later for our picture. Then we see how our microstructure has to be cropped for the desired effect. We want to cut away this area here so that our flow field is nicely visible in the front. We also want to be able to see some of the clustered grains here on the side. So we can see from the axis cross that we have to clip in the direction of the Y-axis from the starting point. We take the small handle at clip Y here with the left mouse and drag it along the axis. In our example, we aim at half of the total length of 250 voxels. We want the clip Y start value to be 125. If we don't hit this exactly with the drag handle, we can correct it with the arrows in the value field here. 3/3 divisions can also be very interesting, as they are more in tune with the golden ratio and create a pleasantly familiar yet exciting relationship. In our case, a half separation is more practical, because then we can still see some of the interesting grains here. Now we switch to the Volume Field tab to adjust the volume field. First, we activate Interpolate Colors here. This softens the colors in the volume fields. This is useful for low resolution volume fields like our training data. But it can also wash out smaller details in the data. With our sample data, it helps us to get a nicer visualization. Now we open the color map. First, we deactivate Apply immediately again, so we don't have to wait for Geodict to update after every change. What we see immediately is that we have flow values for the areas where there is solid material. I'm going to show you how to change that and then explain why that's not a good idea from a visualization point of view. But first, we adjust the transparency transfer function so that we can better see the flow in the pores that is currently obscured by the values in the solid materials. For this, we add 2 more points in the transparency section here and here by right-clicking in the free space and choosing Add Point. Then we select the first point and set its opacity value to 0.3 here on the right side. We select the second point and set its opacity value to 0.8. We also change the position value of this point to 6 here. We select the third point and set its opacity value to 0.99. We also change the position value of this point to 12. Finally, we select the last point and set its opacity value to 0.99. From our adapted transparency transfer function, we can see that the opacity is very low for the slow flow velocities. And with increasing flow velocity, the values become more and more opaque, thus more visible. Now we press apply and have a look at the result. At this point, it should be said that these values are only guidelines. I recommend to save the values either via the dialog saving function or the visualization settings, and then to experiment a bit more. For now, we can identify the pore space and the speed of the flow in it very well. We can also see the depth at which the pore tunnels are located. We don't even have to move the camera. The reason for this is the light absorption when the transparency of the volume field is switched on. The deeper a pore tunnel is located in the volume field, the bluer it is colored by the values in front of it. We encounter this effect almost daily when we look at distant objects. Due to the ozone in our atmosphere, distant objects are colored bluish. We can make use of this familiar effect here to help the viewer with the depth perception of the data. For comparison, we'll now display the flow exclusively in the pore space. We close the color map and have a look at the visibility drop-down menu here in the volume field tab. From this list we can now select on which material IDs the volume should be visible. We deactivate all solid material IDs 1, 2 and 5 and leave it active for the pore space on material ID 0. With a click in the visualization area, we close the drop-down menu and apply the change. We see that now we only see the flow in the pores. This is the more correct representation, but at the same time we can orientate ourselves much worse in the picture. Due to the missing depth perception, the image is now way harder to read. We activate the visibility of the solid materials again via the visibility drop-down menu here. And as we can see again, the depth perception is way better with the activated solid materials. Now we already have a pretty solid visualization of our flow simulation here, but we can amplify our flow visualization with another feature, the streamlines. In the visualization panel, we can enable the streamline visualization by checking the box next to the tab name Streamlines here. Streamlines are the trajectories of the theoretical massless particles that are carried along by the flow. We see one, maybe two streamlines, and it appears as if nothing has changed. We briefly hide the volume field in order to identify the few existing streamlines. For this purpose, we uncheck the box next to the volume field tab name. This sparse distribution of streamlines is due to the fact that the streamlines are getting distributed in a regular 2D pattern in the inflow direction. Since we have only a few pore inputs in the direction of the flow here, only a few streamlines find their way into the inside of our microstructure. In order to increase the streamline density, we change the type of the placement parameter. For the drop-down menu placement here, instead of inflow plane, we select 3D box. This type distributes the streamlines all around the volume of the domain. This improves it, but we still have to do some adjustments. For the fine-tuning of the streamline distribution, we open the visualization settings with the gear symbol in the lower right corner of the tab here. This automatically navigates us to the right place inside the visualization settings tree, where we can adjust the advanced settings for the streamlines. We open the tree placement, box placement. Here we can adjust the sampling density of the streamlines for the X, Y and Z direction. Then we change the value for count X to 10, for count Y to 10 and for count Z to 200 respectively. The values determine how many streamlines per direction are sampled on the 3D grid. As we can see, we have a much nicer and denser streamline visualization now. The streamlines seem very extreme at the moment. When we zoom in, we notice that the apparent thickness of the streamlines decreases, even to the point that we can identify individual streamlines here. This is due to the fact that streamlines are rendered on a pixel base. The line thickness is a value in absolute pixels. That means no matter how high the resolution of the visualization area or the image is, a streamline will always occupy the line thickness in pixels. So at very high resolutions, the streamlines will be optically thinner, at very low resolutions, optically thicker. Instead of streamlines, we can also select stream tubes for the line style, up here in the Streamlines tab. This will take a second to compute. Unlike streamlines, which are 2D lines, stream tubes are actual 3D objects. They have an absolute thickness that does not depend on the resolution and a nice surface shading with shadows and gloss. But they need much more calculation time, as we just saw. If you want to use stream tubes, I recommend to find good settings for the streamlines first and then switch to stream tubes for the image. Now let's have a look at the last line style, Streamlets, here. You can see that the previously grayed out play button has been activated, and when we press it, we get an animated little streamlines. The streamlets allow us to visualize flow direction and flow speed interactively in the visualization area. We can also use this for nice animations in videos. For our image setup, we change the line style back to streamlines. We set the line thickness to 2.0 if not already set. Because of the high number of streamlines and the resolution of the image, this should result in a nice picture at the end. We also unhide the volume field again by checking the box in the volume field tab. The last adjustment we are going to make is the setup of the volume field legend here on the right side in the visualization area. We open the Legends Overlay tree in the visualization settings, open it before, if not already done, and activate the volume field legend. Before we did not pay attention to it and even hid it. But now we would like to give the viewer additional information about our flow simulation. The volume field legend presents information about the name, the units, color coding of the value range and additional information about the minima and maxima. To ensure that the volume field legend meets our aesthetic requirements, which we have predefined with a lot of work for the microstructure and the volume field, we are now adjusting it. To do this, we open the volume field legend 3 in the visualization settings by clicking on the arrow here. From top to bottom in the order, we can now adjust the position of the legend, define the stretch at the selected side, adjust the number of decimal points, adjust the number format to different industry standards, show and hide the plot ranges, and define the thick mark mode by ourselves if we change it to manual. I will now apply the settings as they are shown here. This gives us a nice slim volume field legend that doesn't steal the show from our simulation result, but completes it. We also positioned it at the top because we will save the image with an additional image element in the lower right corner. With this last image element defined and set, we will now see if we can reactivate the additional visualization features in the Camera tab. We switch to the Camera tab now and show outlines and global lighting unfortunately do not work very well in conjunction with such an extreme setup as we have it here, with a transparent volume field and streamlines. But a very useful option that we can activate is the show halo function, which renders a small halo around objects, which can drastically improve depth perception. Now, last but not least, we want to save the created image. This time, we'll not use the image save dialog, but the GeoApp Easy Image. It was created by the marketing team of Mass2Market and was designed to create beautiful marketing material quickly, easily and consistently. The GeoApp Easy Image can be found in the menu under GeoApp Easy Image here. Down here we can now start the GeoApp Easy Image with a click on Run. Easy Image guides the user through the process of image creation, making sure that all the data necessary to create the image is secured. Helping with the image creation process itself, the marketing team of Mass2Market created presets to create beautiful, recognizable images. Among the presets are also special effects, such as the Split by Material preset. We will take a closer look at this in a moment. First of all, let's go through the UI of Easy Image. In the upper section, Image Setup, we can find all the settings for creating the image. Here you can give the image a recognizable name, in this case maybe Flow in Crane Microstructure. This name will also be used as the name for the folder in that all data is saved in. To the name you can choose a prefix and suffix here. These are only added to the files. Maybe you want to create several images for one setup. As suffix we could choose here which streamlines. Then you can select an image preset here. We select the website showroom image preset. Here, Geodict creates a 2D image in addition to the 3D image and composes both images together. We want to keep the colors for Material ID colors, we select Keep. For the input settings mode, we can choose whether we want to create an image quickly with the quick mode, with the default values, or with the expert mode to change some settings. First, we select the quick mode. In the section Save Files, we can select the save folder. Here the project folder is selected by default. We leave the check marks, create a folder to store the data and save Geodict files as they are. For the overwrite mode, we leave Ask for Action. This way we can make sure not to overwrite files by mistake. For the description, we can write an explanatory text for our future self or our colleagues. This text will be saved under the image name as text file. Finally, we can choose to reset the viewport to the current state after the image has been created. We don't want that for now. Now we can press OK and get to the Save dialog for further files. Here we can save any simulation results that were used in the creation of this image and copy them to the resulting folder. This allows us to have all files to recreate the image in one place. For this purpose we click on Browse here, go to the subfolder Part 2 and choose the Lear-Stokes result.gdr by double-clicking. This will result in the simulation result being copied to the resulting image folder. The used volume field can be saved separately down here, without the need to copy the whole simulation result folder. We click OK. Now Easy Image creates the image and we wait a short moment till it has finished the job. We open our project folder again and open the newly created subfolder Flow in Crane Microstructure, where we can find our image and the additional data that has been stored. First we look at our final image here. On the one hand we have our microstructure with volume field and fine streamlines here, and there the 2D representation down here. We close the image and see that we have saved the 2D and 3D image separately here and here. In addition, the structure here, the flow field here, and the .gdr here with its result folder here we saved. Finally, we have a Python file here in which the settings are saved with which the image was taken. EasyImage has not only saved our image, but also all data necessary to retake the image. We close the folder and go back to Geodict. As a conclusion for the second part of this workshop, we will have a look at another preset of EasyImage, the Split by Materials preset. The Split by Materials preset divides the microstructure based on the different material IDs and visualizes them evenly distributed, similar to an exploded view diagram. This way, the different materials within the microstructure can be evaluated side by side. The splitting process can also be visualized in the form of a video. If not already open, we click on GeoApp in the menu and select EasyImage. It opens here in the setup area and we click Run to start. First, we enter the name in the image name field under which we want to save our image and/or animation. We name it My Split by Material Animation. For the image presets, we choose the Split Structure by Material preset. We want to keep our material ID colors and we select Keep. For the input settings mode, we select Expert Mode. This gives us more control over the output in the setup. The rest of the setup fits so far. A folder is created where all necessary data is stored to restore the image and the animation, and we click OK. In this dialog again, we can store additional data to reproduce the image, and we click OK. In this dialog, we will now decide how the split is to be set up. By default, the microstructure is split in Z direction. The offset axis value plus the offset type indicates by how many voxels the materials are shifted. Increment in voxel will move each material by the specified values of the offset X, Y, and Z axis. With the current microstructure, this would mean that we would end up with a 250 by 250 by 750 voxels domain size at the end. Depending on our hardware, we scale down the microstructure under downscale structure and times. This reduces the resolution of the microstructure, but also reduces the main memory requirements. For our example, we will move the materials on the x-axis by 300 voxels incrementally. This gives us an extra 50 voxel wide gap between the different materials so that we can clearly distinguish the materials. We also choose a negative direction so that the clustered grains will be moved to the front, not the back. In the animation options, we select 60 for animation over n frames. This produces a short 2-second video. Of course, longer videos can be very interesting, but for this workshop, we want to get a quick result. We leave the animation curve style at east. That gives us a nice flowing animation. USteady-Axis Zoom pre-calculates the camera zoom so that the final split microstructure fits into the visualization area from the beginning. If this function is deactivated, the camera will be adjusted with every frame. The result is a zoom effect for the camera. We uncheck USteady-Axis Zoom, if not already unchecked, to get a nice zoom effect. For the zoom multiplier, we can select the number greater than 1 to zoom out further, or less than 1 to keep the camera closer to the microstructure. A value of 0.6 will work for our example. We click OK. In this dialog, we can choose which material IDs we want to see in the split. For example, you can hide overlapping materials or show the pore space. For this example, we leave it at the pre-selection. We click OK. And we wait briefly until the microstructure has been split into the different materials. In this dialog, we can now select the visualization settings. Basically, the default settings are already suitable. For more pleasant visualization, set the structure renderer to smooth and activate the global lighting. We will choose the faster render method for this workshop by selecting the structure renderer to box and deactivating the global lighting. For the width and height in the image setup, we take a full HD resolution 1920 by 1080. Crop white space and transparency is ignored for the video, because the video needs a stable image resolution and videos can't have a transparent background. We uncheck them both and click OK. The video is now generated. Depending on the visualization settings and the resolution of the microstructure, this may take some time. I will now fast forward so we can look at the result. Since we are practically at the end of part 2, you can let the animation run. It should be finished till the start of part 3. To view the video, I open up the project folder, navigate to the My Split by Material Animation subfolder and open the video. And there we have our result. The microstructure is pulled apart in X direction and the whole video takes 2 seconds. With Layer Geo, we could have achieved the same effect by hand and a lot of time. Good thing Easy Image did it for us. We close the video and look at the image that was created. It shows the final result of the material split. And that concludes part 2 of the workshop, in which we looked at how we can present simulation results in an aesthetic and informative way. In addition, we got to know Easy Image and saved our image about it. As a bonus, we used another Easy Image preset, which split up the structure based on the materials in a nice video. We leave Geodict open and return here after the questions and the break.